Okay, ET 114, Chapter 15, continued with the notes. Section 5 is the impedance diagram. So, for impedances in series, we treat the impedances just like resistors. Same formulas. You take to get the total impedance, you just add the impedances together. Okay, and that would be in ohms, the impedance. The magnitude is in ohms. The phase angle is going to be in degrees. And to find the current, you use Ohm's law. E equals I divided by the total impedance, ET. I is the current in loop in amps. And to get the voltage drop across an element, you take the current going through that element times the impedance of that element. Then voltage is in volts, impedance is in ohms. The actual impedance diagram looks like this, where you have a vertical axis and a horizontal axis. The vertical axis is called the J-axis, or the imaginary axis, and that is going to be when you have a complex number and you have the value x, so you're going to have a complex number z equals r plus j x. Okay, so R is going to be the resistance component on the plus or real or horizontal axis going along here, that value. And then on the vertical axis, you're going to have the X value, which is, going to go along here. This is showing you, and a pure inductor has X abel angle 90, so it's going straight up. The angle starts at the positive x-axis, the positive horizontal axis, I should say, and then it goes clockwise from there. A pure capacitor has x of c angle of negative 90. That should be a negative. It's kind of hard to see in there. And then a pure resistor has r angle of 0 degrees. Okay, so same formulas as we learned in DC circuits apply to AC circuits. You have KVL, which is Kirchhoff's voltage law, which is the sum of the rises, the voltage rises in a loop equals the sum of the voltage drops. The power delivered in the circuit in watts is equal to E times I times cosine of theta t, which is equal to E times I times cosine of the value theta v minus theta I. Okay, and then theta t is sometimes referred to as just theta, which equals the absolute value of theta v minus theta I. It's the phase angle between the voltage and current waveforms in degrees or radians. FP or PF, I like PF, but I think the book uses F sub P, equals cosine of theta t, which is the power factor, which is dimensionless. It's just a measurement of how in unity the circuit is. And it's also equal to R divided by ZT, which ZT is the total impedance in the circuit in ohms, and R is the resistance in the circuit in ohms. If theta V is greater than theta I, then the power factor is lagging. The current lags the voltage, and it's inductive. Remember Eli the Iceman, so if you have the voltage leading the current E before I, it's L, which is inductive. If theta I is greater than theta V, then the power factor is leading, which means the current leads the voltage. It's capacitive, and remember ice, that the current is before the voltage. So the current is leading the voltage with the capacitor C, and the current lags voltage, it's after it with an inductor L. So I developed a procedure for solving series of parallel circuits, and it just goes through. There's how many steps in here? About 6 steps. If there's any voltage current given in sinusoidal form, they need to be converted to form polar notation. So you would take these two equations, and you run it through these equations to convert the phasor form, and then you find the total impedance of the circuit. You have to convert each individual element into its polar or rectangular forms, and then you would sum them together. It's easier to do summing in add and subtract in rectangular than in polar is easier to multiply and divide. So if you have to add together, you would convert each element into its rectangular form, add them together, and then you could do your calculations that way. And then if you had to do any division, you would convert them to their polar forms and then do that. Then use series and parallel combinations of impedances to find the total impedance. So series, you just add them together. Parallel, which is going to be the next chapter, we just use the parallel formula. This is two impedances in parallel here. And then you use Ohm's law to figure out the voltage or current, whatever you're looking for. Remember, V equals IZ. You have to use the phasor form, and the polar form works better for multiplication and division. Once the voltages and currents are calculated, then you can tell whether a circuit is leading or lagging by the following. Voltage of phasor equals this, where V and I are the magnitude RMS value of the phasor. Current phasor is equal to this. So theta V and theta I are phase angles. So theta T equals the absolute value of theta V minus theta I is the total phase angle difference. If theta V is greater than theta I, then it's Eli, meaning the current comes before the voltage. Current lags by theta T, it's inductive. If theta I is greater than theta V, then it's ice. Current leads by theta T, capacitive. Note, the angles can be negative and the sign stays with the angle. So if you have this example, the phase angle of this waveform is negative 30, and then the power you calculate by these formula, power factor with this formula, and then you can convert voltage and current in the phasor form back to sinusoidal form by reversing the process in step 1. So you have the phasor form of the voltage and current this way, and you would convert them by taking the RMS values and multiplying by the square root of 2, and you take the same phase angle. And then the frequency F is either given or found with the formula angular velocity equals omega equals 2 pi F. Whatever is in between the sine and the t is omega. So examples of this: sine of 5,000 pi times the square root of 2 divided by 3t plus 30. So omega is equal to 5,000 pi times the square root of 2 divided by 3. So that kind of goes through this procedure. I'm not going to go through it again, but it just tells you the big equations to remember are these two. You have the reactance of an inductor equals omega L equals 2 pi FL. And the reactance of a capacitor equals 1 divided by omega C equals 1 divided by 2 pi FC. Remember, this omega C and 2 pi FC are both in the denominator. Okay, so when you put it into your calculator, you want to make sure that you put parentheses around it so it knows that. The voltage divider, it's the same as in DC circuits. So the voltage across one or more elements, Vx, that have a total impedance of Zx. So the voltage across a single element equals the total voltage appearing across the series circuit times Zx divided by Zt, which is the total impedance in the series circuit. And then the frequency responses for series circuits, you have a resistor, which is not going to change resistance with frequency. You have X of L, which is going to be linear with frequency. And you have X of C. If you plug it into this equation, it's going to be a decaying curve like this. So these are the impedances on the impedance diagram that you guys saw before. And then the book just goes through a RC circuit and it calculates the total impedance of an RC circuit here, and then it calculates the voltage across the capacitor and the phase angle of capacitor, the capacitor phasor, which is theta sub c, and you can see that the voltage or the impedance Z sub t, as changed with frequency, gets very, very small, Z sub t. So then the voltage, as the frequency increases across the capacitor, is also going to get really small. It's going to follow that. And the phase angle starts off as 0 and it goes to almost negative 90 at the high frequencies. So likewise for an RL circuit, you have the total impedance calculated here, and then you have the impedance diagram, and then the impedance of the entire circuit. It starts off a value R and it goes up basically in a straight line from there. And then the voltage across the inductor is going to rise up as frequency increases to the maximum value of E. And the phase angle in a similar fashion goes up to just about positive 90. And then you have the same thing for an RLC circuit. It talks about the frequency point of inflection where XC equals X sub L. And then it talks about, we're going to start talking about, this looks like filters in here. So for the conclusions of this chapter, the total impedance will be frequency dependent with reactive elements. The impedance of any one element could be greater than the total impedance of the network. The inductive, because now we're dealing with frequencies. The inductive and capacitive reactances are always in direct opposition on an impedance diagram. Depending on the frequency applied, the same circuit can be either predominantly inductive or predominantly capacitive. At lower frequencies, the capacitive elements will usually have the most impact on total impedance, while at high frequencies, the inductive elements will usually have the most impact. The magnitude of the voltage across any one element could be greater than the applied voltage. The magnitude of the voltage across an element compared to the other elements of the circuit is directly related to the magnitude of its impedance. So the larger the impedance of an element, the larger the magnitude of the voltage across the element. The voltage across a coil or capacitor are always in direct opposition on a phasor diagram. So we're saying that a coil is the same thing as saying an inductor. The current is always in phase with the voltage across the resistive elements, lags the voltage across inductive elements by 90, and leads the voltage across all capacitive elements by 90. And the last conclusion, the larger the resistive element of a circuit compared to the net reactive impedance, the closer the power factor is to unity. So a unity power factor would be fully resistive, which means the inductive and the capacitive elements are balancing each other out. And then the last section in the book, it just shows you how to connect an oscilloscope and measure phase angle. And it's showing that there's an actual phase difference between, if you look at this zero crossing and this zero crossing, you could see that there's that the current is leading. In this example, it's leading the voltage, and it goes through some calculations here.